First, here are the papers my talk will be based on. And I would like to take this opportunity to thank all of my co-authors, amazing co-authors, some of whom I see are in this room. So big thanks, big shout out to all of you. I think we did some very cool work together. And now, let's talk about this work. So, as I mentioned, I will talk about adaptivity, adaptiveness, and, well, first I should probably explain what I mean by this. So, by adaptiveness, I mean how can we use pre-trained neural networks in new situations? How can we use them for new data, for new tasks, for new data distributions, and so on, right? And I think this problem, is very important right now, given how the machine learning systems develop currently. So on this plot, on the x-axis, you can see the year of production of certain machine learning systems, and on the y-axis, you can see the cost of training those systems. And if you look closely, the y-axis is in logarithmic scale, which means that the cost grows exponentially. So basically, it doesn't make sense to train a new model every time you encounter a situation, a task that you haven't seen in your pre-training. It makes much more sense to, take your pre-trained neural network and adapt it to this new setting in some way. Okay. So yeah, as I mentioned, I will talk mostly about fine-tuning and reinforcement learning. And, well, you might be wondering what fine-tuning is, if you are not very familiar with those topics. And you might also be wondering what reinforcement learning is. So I will try to explain those terms first before proceeding so that we have, a common understanding of those terms. So let's start with reinforcement learning. And I will try to explain this one basically by contrast. So you might be familiar with supervised learning. This is like the most common paradigm for deep learning currently. And here we have some static data set that contains some observations and some targets. And the goal of your model is to basically, based on a certain observation, predict the target, right? And some examples of such systems are large language models. Here, your data set is basically the whole internet. Your observation is the sequence of words observed so far, and the target is the next word in the sequence. And with this fairly simple objective, we can get amazing results as we have all seen in the past few years. Another example of a supervised learning system are image classifiers. Here you can imagine that the observation would be, an image, and the target would tell us what is in the image. So here you could try to train a model that predicts what type of a bird is in a given image. In contrast, in reinforcement learning, we don't have this single direction from the data set to the model. Instead, we have this loop. So we have the environment that gives us the state, which basically tells us what is currently going on in the environment, and the reward, which tells us how well we are doing currently. And then we have the model, which tries to, based on the states, try to give actions such that in the end we will maximize the rewards. And examples of systems that you can try to solve with reinforcement learning are games. So in this case, we have the classic Arkanoid game. The goal is to break all of the blocks with the ball. And here, the environment is your game. The state is the current frame of your game, so what we are currently seeing on the screen. And the reward would be the score. This tells you how well you are doing. And, well, the actions are basically, there are three possible actions: go left, go right, or stay where you are. And here, we would hope that the model, through this interaction with the environment, would learn to find a behavior that allows us to basically break all of the blocks in this game, right? A more practical example of something you might use reinforcement learning for are robotic tasks. Here the environment is the robotic arm and, well, everything around it. The states would be the positions of all of the objects in the environment, and the reward is how close you are to achieving a certain goal. For example, this goal would be pushing an object to the target position. And the actions are, how do you move this arm? And again, we would hope that through this interaction of the environment and the model, we would learn how to achieve this goal reliably, right? So in supervised learning, there is like this single arrow going from the data set to the model. In reinforcement learning, we have this constant loop, which makes things more interesting, I would say. Okay, so now to the second question, second part of the topic, what is fine-tuning? This one is, I think, a little bit simpler. So it basically means that we take our pre-trained model and we continue training it on the new data that we encounter. And the main reason to do that is knowledge transfer. Basically, we can hypothesize that during the pre-training, we saw some data that would be useful for the fine-tuning task. And this means that if we were to use this pre-trained model as the starting point for our training procedure, we will get good results much, much quicker than if we were to start training from scratch, from random initialization. So this is also very, very common in large language models, foundation models. One example of such fine-tuning procedure would be on some mathematical task. The intuition is that during your pre-training you saw a lot of mathematical data, and this knowledge can then be used to train on a particular mathematical task much more efficiently. Okay. Okay, so we know what fine-tuning is, we know what reinforcement learning is, so the only question that remains now is basically why? Why should we bother about fine-tuning in reinforcement learning? And I would like to answer this question by listing some of the pros and cons of both supervised learning and reinforcement learning. So for supervised learning, I think the main advantage is that it scales very, very nicely. We have this stable learning procedure. We can achieve amazing things just by scaling up our data set, scaling up our models. And GPT-4 is basically a great example of what we can do with this kind of approach. I would say that a major disadvantage of supervised learning is that the data is more or less the ceiling, right? You cannot get much better than the data that you have. On the other hand, in reinforcement learning, there is no ceiling because we are optimizing for a certain reward. You want to maximize this reward. You can do this for as long as you want, and at some point maybe you would get superhuman performance. Unfortunately, reinforcement learning is hard to scale. It is very unstable because of this loop going back between the environment and the model. So one possible idea to try to get the best of both worlds here would be to start with supervised pre-training, which we know can scale up very, very well, and then fine-tune such models with RL fine-tuning, right? So we get both nice scaling properties in pre-training and then this endless improvement in fine-tuning. Okay. Unfortunately, there are certain problems with fine-tuning. And one of the major problems is forgetting or forgetfulness. So imagine that you have 3 tasks. Let's say they are robotic tasks. In the first task, the robot has to use the hammer to hammer in a nail. In the second, it has to push an object to a certain location. In the third task, it has to close a faucet. Okay? And let's imagine that we want to train on those 3 tasks in sequence. We first train on the first task. We use the parameters that we get from training on the first task as a starting point for training the second task. And then we do the same for the third task. So we train in sequence. And what we will usually see in this scenario is something like we see in this plot. So we train on the first task, it goes very well. The blue bar is pretty high. But as we go to the second task, we are able to learn the second task pretty well. the red bar, again, is high, but the blue bar starts to kind of fall down. And then, as we go to the third task, again, we are able to learn the third task very reliably, but we lose the performance on the first and the second task. This phenomenon is called catastrophic forgetting, and it basically means that the network rapidly loses performance on prior tasks after we change to a different task. Our networks forget the data that they haven't seen for a while. And the field of continual learning studies this phenomenon. So there have been multiple studies of this problem in the context of supervised learning, but in the context of reinforcement learning, not so much. So this is something that we really wanted to investigate, that we really wanted to understand. And for that purpose, we introduced the continual word benchmark. This benchmark consists of 10 tasks that we train on in sequence, right? So we start with the first task, hammering in a nail. After training on this, we go to the second task where we push an object, and so on, and so on, and so on. Right, so we train on this whole sequence. And after we finish training, we check two major metrics. First of all, we check forgetting, so how much performance we lost on the preceding tasks. Basically, after all these tasks, can we still remember how to hammer in a nail? And we also look at knowledge transfer, which, as you might remember, is the main motivation for doing fine-tuning in the first place. This tells us, how much we actually gain from previous tasks when training on a new task, right? Can we use this knowledge to train more efficiently? And we test multiple continual learning methods here that were previously used to deal with forgetting in the supervised learning context, but were not so well tested in reinforcement learning. So what we found out is that there is this huge tension between knowledge transfer and forgetting. The continual learning methods that we tested were able to stop forgetting, but at the same time, they also stopped any kind of transfer. This basically meant that even though we were able to retain the knowledge, this knowledge didn't help us to really learn the new task any better than if we were to train on them from scratch, which again kind of defeats the purpose of fine-tuning. So, now the question is how to solve this. And we found out that exploration is very important for efficient transfer. So basically, once you start a new task, you should use your previous behaviors to gather data on this new task. And another insight is that it turns out that supervised learning objectives work much better at minimizing forgetting than reinforcement learning objectives. So doing this kind of combination between supervised learning and reinforcement learning really helped us to stabilize this process and get both knowledge transfer and minimize forgetting. And yeah, thanks due to combining those insights, we were able to propose this method called CloneX-SAC that performed very well both in transfer and forgetting. And at the same time, I would like to mention that our benchmark was then used for experimental analysis by other people. So other people tested the continual learning methods on this benchmark. Yeah. Okay. So here in this scenario, we have this very obvious change, right? So we start with the first task. We train for a bit, then we change the task to train on the second task. There is this obvious shift of what we are training on. So now we turn to the question, can you actually observe forgetting if you do not change the environment, right? So can you still observe forgetting if you keep fine-tuning on the same environment that you pre-trained on? And as it turns out, there is a particular setting when this happens. So this happens when you pre-train with supervised learning, but then you try to fine-tune with reinforcement learning. So again, this is exactly the setting that I proposed as a best of both worlds a few slides ago. So in order to understand this, let's imagine a video game that has two levels. And let's imagine that during the pre-training, we trained on a data set that had both of those levels in equal distribution, right? So basically 50-50, first level, second level. So we train on this distribution, and we get a model that behaves as in this cartoonish example. So we get a model that is basically almost perfect everywhere, right? Why almost perfect? Because in practice, it is extremely difficult to clone your data perfectly. There will always be some very small mistakes, and those mistakes tend to accumulate. What it means in practice is that when we run this, our pre-trained model in this environment, it will sometimes die on the first level, and it will not see the second level, right? So if we were to look at how the distribution, data distribution would look during the fine-tuning, at the beginning of the fine-tuning, then we would see much more examples of the first level than the second level, because we kind of keep dying in the first level. And this shift of the data distribution will again lead to forgetting, even though the environment is still the same. We only change the way of how we basically sample from this environment. And yeah, so here's basically a cartoon of what happens. We start with this model that is pretty okay everywhere, but as we start fine-tuning, we only see the data from the first level. Because of that, we are able to learn on the first level quite reliably, but we forget how to perform on the second level because we don't see the data from the second level, right? And here's an empirical proof of what I just said. So here we test this hypothesis on this challenging NetHack game. You see basically here we see this basically the same plot as before, but now we have more levels. And as you can see, our pre-trained model, the orange bars, our pre-trained model sees the later levels much less often than how often those levels were present in the data set, which is represented by the blue bars, right? So for example, for the 6th level, we don't see it very often when we run the pre-trained policy, but we see it very often in our data set. Okay, so here's what happens. So, here's the representation of what is going on here. We get this policy that is pretty okay everywhere. And again, as we try to just simply fine-tune on this environment, we get some terrible results. So here the blue line is what happens if you try to fine-tune this without any additional tricks. And basically the training procedure kind of deteriorates, right? You get very poor performance, which again corresponds to this cartoon that I've just shown you. And obviously this is a problem, right? We would hope that we can use our pre-trained model, we can fine-tune it with reinforcement learning and then get this, let's say, superhuman performance, right? But here, obviously, this is not the case. Fortunately, we can use the methods from continual learning to address the forgetting problem, just as we did in the previous part of this presentation with the robotic tasks, right? So now, the pink plot here represents fine-tuning with an additional measure for knowledge retention, for avoiding forgetting. If we combine fine-tuning with this continual learning method, then actually we get state-of-the-art performance with 11,000 points, which is around 2 times the score of our pre-trained model. We start from 5,000 points, and if we are careful about how we fine-tune our model, we can get 2 times that, over 2 times that. And I would say that the main takeaway from my talk is that reinforcement learning fine-tuning can really help. In some situations, it can really elevate your pre-trained model to some previously unseen performance. But if you want to do this, you have to be very careful about forgetting. If you are not, then you get the blue curve, and yeah, it's not even better than a model trained from scratch. Okay, so that's the main takeaway. And now for the quick summary. I would argue that given how expensive the training of deep learning models has become, then because of that, we really need to learn how to adapt existing models to new settings so that we are not constantly retraining them. I would argue that online RL fine-tuning is a promising way to do adaptation. But if you want to do online RL fine-tuning, then you have to be careful about forgetting. You have to basically make sure that forgetting doesn't hinder the fine-tuning process. And finally, I would like to mention that My current research question that I want to explore is how to adapt large language models for decision making, right? So basically how to take a model such as GPT-4, such as Llama, and use it for some decision making tasks, which might require interaction with complex environments. And that's all. Thank you for your attention.